Okay, so now that we're pretty good at doing Lewis structures, actually we're getting really good at it from what I've seen on your quiz yesterday, and we tend to think, all right, I got it now. And then something like this comes about. All right, so here's a little curveball. Models that we're using, for example, this Lewis structure model, are human inventions. So what we're doing here, we have a human invention to try and explain something that occurs that we can't physically see. So we create a model, and again, they're oftentimes useful. We've been able to predict polarity, we've been able to predict bond angles and things between atoms that we can't hold in our hand. This idea of the Vesper theory, so we're getting pretty good at it, as I said. But it does not equal reality. This is not what structures are going to look like if we could look at it, hold it in our hand. For example, there's the structure that we've done for CH4. We have the 3D structure. We have 109.5 degree bond angle, and all of that from the Vesper theory. 4 bonding, 0 non-bonding, and the fact that this is nonpolar. So we were able to do all of that from the formula CH4 by writing these Lewis structures. But they're often wrong. And the reason is they're based on oversimplifications and these assumptions that tend to not be exactly three-dimensional reality. They tend to become more complex as they age because they have to be sort of patched. So you have to sort of add exceptions and then exceptions to exceptions and then exceptions to exceptions to exceptions, and they become more complicated. All right, so for a model to be used properly then, you have to understand its limitations, and then when it's wrong, sometimes we learn even more about it. All right, so where am I getting at with this? So we're going to talk about something called resonance. And it looks simple enough to start with. So what we're going to do is we're going to draw the Lewis structure for nitrate. So NO3 is the polyatomic ion nitrate. And what we've learned to do so far is count the number of electrons. So 5 plus 18 and then plus 1 for the negative charge gives us 24 electrons. All right, so nothing new there. And in the middle, bond it to the O's, finish the octet of the O's. Count how many electrons I've used. I've used 24, 8, 8, and 8. Remember, when it's an ion, we put it in brackets. And then we check to see if the central atom has its octet. And it does not. And nitrate does need 8 around it. And so what we've learned to deal with here, it's already one little patch to our Lewis structure, is how do we deal with that? Well, what we've learned is we're going to take one of the non-bonding pairs and make them a bonding pair. And so my structure becomes nitrate or nitrogen with a double bond to that oxygen, which now only has 4 extra pairs around it, and these remain unchanged. So I have that one and that one. So now I have that Lewis structure. Well, when a resonance structure means anytime you make a double bond and you have another option, that creates a new structure. So for example, in this one, I did this left-hand oxygen as a double bond. But I could have just as easily, going back over here, done the right-hand one, or even the bottom one. So I end up with that structure if I do the left-hand one. I end up with this structure if I do the right-hand one. Or even this one if I do the bottom one. So O, O, and again, minus 1. All right, so what's the difference between them? Well, really nothing. I mean, we're just changing one or the other. But yeah, there is a difference. And the reason is, which one of these would be correct? Is it going to be the left-hand one? Is it going to be the right-hand one? Is it going to be the bottom one? And the answer is, it's really none of these. And so there's where our model sort of gets more complicated. So if you see what I've done here, I put a double-headed arrow between the Lewis structure and brackets. I kind of ran out of room there and did it down that way. But the double-headed arrow in brackets. And anytime you can write more than one valid structure, you put it in brackets, whether it has a charge or not. So we've learned that you do it when you have a charge. But if you're going to do these resonance structures, then you do it in brackets anyway. And then what's the reality is, according to the structure, there should be 2 different kinds of bonds, right? We had 1 double bond and 2 single bonds. But experiments show there's only 1 kind of bond. So then what's right? Well, what's right is The correct structure for nitrate is none of the ones. So it's none of the ones that we've written, but instead is an average of the three. So, and again, you show it in brackets with a double arrow. And so when they test this nitrate molecule, it's not, two single bonds and one double bond. So it's not two single and one double. Instead, it is three equal bonds. So there's only one kind of bond. So there's an average kind of bond that happens there, maybe a bond and a third, if you will, length between the nitrogens and the oxygens. All right, so that's called a resonance structure that we're going to do with our Lewis structures. And again, you put them in brackets, and you put a double-headed arrow between them. And if there's two, or if there's three, if there's more, for example. All right, now here's one that we've done, and we already did a resonance structure without even realizing it. When I showed you how to create an octet around the central atom when it didn't have one, and you didn't have any more electrons to add. For example, the one we did was carbon dioxide. So we had 4 plus 12 is 16 electrons. When we did the Lewis structure, we did bond to O's, finished the octet of the O's, and we saw right away there's a problem. What the problem was, we've used all 16 electrons, but carbon only has 4 around it. So the way we overcame that was we did a double bond on one side. So we could have, taken this pair and put it in the bond, taken that pair and put it in the bond, so you end up with a double bond on the other side, and you end up with that structure. But when I showed you this, I said, rather than making it look nice and symmetrical, we could have taken another pair from that side and made carbon with a triple bond on one side. So both of these are valid structures. So we would show it like that, a resonance structure. So what if there are completely different Lewis structures, like this one? The first one we did, the nitrate, they weren't really completely different. You just moved the double bond around. But this one, there's two completely different structures. Here we have a double bond on both sides, and here we have a triple bond and a single bond. So two completely different structures. Which one's better? Well, the answer to which one's better lies in something called a formal charge. So we can assign this idea of a formal charge to each atom in the molecule, and then decide, based on its formal charge and following a few rules we're going to talk about, which one is a better or more likely structure. All right, so let's do that. So which one's correct? Well, the way we're going to do that is we're going to assign formal charge. So here's how you do formal charge. And I skipped ahead. I moved my things around. Let me just write it then, since, well, I know it's coming up here. Let me skip ahead one. Here it is. Oops. So formal charge is equal to the number of valence electrons in the free atom minus the number of electrons assigned to the atom inside of the molecule, where the number of assigned is equal to the unshared electrons plus half of the shared. Well, what? All right, well, here you go. Here it is, basic English. All right, so here was our two Lewis structures for carbon dioxide. And we want to see which one is better. So which one is more valid? So again, there they are with the brackets. All right, so here's how it works. This right here, the number of valence electrons in the free atom, this we get right from the periodic table. This is the number that we used when we were counting how many dots does each atom get when we draw the structure. So we're going to look at the periodic table. The number of valence electrons, remember, is equal to the S's and the P's, or just the Roman numeral and the letter A. For example, oxygen is in group 16, so it has 6 free electrons. Carbon is in group 14. It has 4 valence electrons in the free atom when it was all by itself. All right, so let's just jump right in and do the formal charge for this. So I'm going to draw it over here. All right, so there's the structure I want to evaluate. So what I have to do is assign a formal charge to each atom. So here is a doubly bonded oxygen and a doubly bonded oxygen. I usually do the outside ones first, then the center one. So what I want to do is, what is the formal charge going to be on this doubly bonded oxygen? All right, so the number of electrons in the free atom. So the number of electrons in the free atom. For oxygen, it's in group 16, so it has 6 valence electrons, or group 6A, minus the number assigned in the molecule. So now it's doubly bonded to carbon. I want to figure out how many are assigned to it. Well, that is the number of unshared electrons plus 1/2 of the shared. Well, the unshared electrons are, there's 1, 2, 3, 4 unshared electrons around our oxygen. And then there's 2, 4 in the bond. I want half of the shared. So half of 4 is 2. So I have 4 unshared plus 2 shared. So I have 6 minus 4 plus 2. So I get a 0. So I get a 0 formal charge. And what you actually do is write it right on the Lewis structure. Now, this is also a doubly bonded oxygen. So it's going to be 6 minus 1, 2, 3, 4 plus half of 4, which is 2. So this one also gets a 0. So then I got to do the carbon in the center. All right, the carbon in the center, the number of in the free atom again. So the number in the free atom, carbon is in group 14. So it is 4 in the free atom minus the number associated with it in the molecule. So I have how many unshared? Well, I don't have any unshared electrons, so that's 0. Plus half of the shared. So I'm sharing 2, 4, 6, 8. Half of that is 4. 4 minus 4 is 0. So this also gets a 0 formal charge. Now, the best structures, here's the key, the best structures have more zeros. So you can't get any better than this one that we just did because you got a 0, a 0, a 0. And the other part of that is the sum of the formal charges will always equal the overall charge of the molecule. Well, carbon dioxide doesn't have an overall charge. Its charge is 0. So 0 plus 0 plus 0. All right, let's evaluate the second one then. So what about the triply bonded? So we have a triple bonded oxygen, a single bonded oxygen. Let's do the formal charge. All right, so I have a triple bonded O. And a triple bonded O, the number assigned to the free atom is 6 minus the number of unbonded electrons, which is 2, plus half of the bonded. So 2, 4, 6, half of that is 3. 6 minus 5 is a positive 1. So this is going to get a positive 1. Now I have a single bonded oxygen on the other side. All right, number assigned to the free atom. Again, oxygen's in group 16, so 6 minus the number of unbonded electrons, which you could see there is 6, plus half of the bonded. I have 2, so plus 1. 6 minus 7 is a negative 1. So this gets a negative 1 charge. So now I can guess that the carbon in the middle is going to be 0. Why? Well, because CO2 has an overall charge of 0, but I have plus 1 and minus 1, so that has to be a 0. But it's good to do it. So carbon in the center, 4, because the free atom, group 14, minus the number of unshared or non-bonded electrons is 0. I don't have any. I don't have any here in my structure. Plus half of the bonded, 2, 4, 6, 8. Half of that is 4. 4 minus 4 is 0, so you can see that it did work out to be 0. So our other structure had a 0, a 0, a 0. This one has a plus 1, a 0, and a minus 1. And again, the one with more zeros is the better of the two structures. So if I had to choose between a double bonded on both sides or a triple and a single, I'm going to go with the double bonded because it had more zeros. All right. Now, when is this going to happen? How am I going to know that I can do resonance? And the key to that is what we talked about here with, let me expand my periodic table here. What we talked about here in terms of expanded octets. Remember, there were some exceptions, just like anything else. The first column here, they did not need an octet. They were happy with 2 electrons. The second one, remember, was happy with 4 electrons. And then that one, we're never going to do these because they're ionic bonds. They had 6 electrons. But anything from here over had to have 8 electrons around it in order to be a valid Lewis structure. But then in addition to that, the third row of the periodic table or lower, so from silicon on down, these could have, remember, more than 8. In fact, they could have 8, they could have 10, or they could have 12 in all of the molecules that we've done. And you're going to see that you can actually do some Lewis structures with 14 or even with 16 when you're, again, doing the Lewis structures because of these expanded octets. So let's consider, what did I do with it? I should have a sulfate here somewhere. And I must have lost it. Let me just jump to this one, and I'll do it from here. All right, so SO4 minus 2 is what I want to do. Okay, so SO4 minus 2. The directions on your homework assignment for tonight is draw two valid structures and then do the formal charge and indicate which one's better. All right, so just start the way we did it on our quiz. So 6 plus 24 plus 2 is 32 electrons. If you can't do this part, go watch the one on Lewis structures. All right, so sulfur in the middle, bonded to 4 O's. Finish the octet of the O's. And we've used up all 32 electrons. It has a charge, so remember a bracket, the charge, and we're good. And that would have made us happy on our quiz. 4 bonding, 0 non-polar, tetrahedral shape, 109.5 bond angle. We can tell sp3 hybridization. We got all kinds of things we know about that. All right, so what we learned today then is if I'm asking you or telling you that this has a resonance structure, and you could predict it could, how? Well, look where sulfur is on your periodic table. What we just talked about. Sulfur is, right here. It's on the 3rd row of the periodic table or lower. So any of these can have, more than 8. They can have up to 10 or 12 electrons and be valid. So one resonance structure would be, all right, so we're going to take a non-bonding pair and put it into the bond. So 1, 2 bonds. Now we don't have 6 around it. We took some and we placed it into the bond. So pay attention to your electrons, as I got scolded today in first period when I didn't fix it. Very good. So there's one valid structure. How about another one? Well, another one might be, instead of just doing it once, do it twice. So take this pair and stick it into the bond also. So now I have a structure that looks like that. And again, remember to get your electrons correct on the outside. So I know I'm running out of space over there, but there you have it. Okay, so now which of these three is the best one? Was it the original one that I did, where you just had 4 and 0 and you had all single bonds? Is it one double bond? Is it 2 double bonds? Is it a triple bond? And again, we can now assign these things formal charge. So I'll work my way across, and then we shall see which one's the best. All right, so what I want to do is the outside ones first. So I don't have, all my outside ones here are single bonded oxygens. So in a single bonded oxygen, it's the number of electrons assigned to the free atom, which is 6, minus the number assigned to it in the molecule, which is 1, 2, 3, 4, 5, 6 non-bonded, plus half of the bonded. It's a single bond, so that's 2. So plus 1. So 6 minus 7 is -1. So that gets a -1. Now, all of these are also singly bonded oxygens. So I'm going to end up with -1 on all those, because they're going to be exactly the same as that. So now I have sulfur in the middle. The sulfur in the middle is going to be 6 minus the number assigned to the free, or the number of unbonded electrons, which is 0, plus half of the bonded, 2, 4, 6, 8. 6 minus 4 is a +2, so +2. I guess they'll give up eventually. I see I'm not going to answer. Maybe not. All right, this one. So now, again, I have a singly bonded oxygen. A single bonded oxygen is going to give me 6 for the free atom, minus the number of non-bonded electrons, which is 6, plus 1/2 of the bonded. There's 2, so +1. 6 minus 7 is -1, so that gets a -1. This would get a -1. That gets a -1. This is a double bonded oxygen, though. So a double bonded O, 6 minus 1, 2, 3, 1, 2, 3, 4 non-bonded. 4 bonded, half of that is 2. 6 minus 6, I get a 0 on that. So a 0 on that one. And now the central atom, S, 6 minus the number of non-bonded, which is 0, plus 2, 4, 6, 8, 10. Half of the bonded is 5. 6 minus 5 is +1, +1. Remember I said about an overall charge adding up to the overall charge. So, you add those up and you get a -2. You add these up over here and you get a -2. This one's definitely better than that one because I got a 0. Remember, the more zeros, the better. This one is going to end up 0, 0, -1, -1, and 0. All right, so which is the best out of the 3? Well, this one has 3 zeros, so this would be, according to the formal charge, the best, or the better, I guess, We don't necessarily know if it's the best, but it's the better of the 3 that we have or the best of the 3 that we have. We don't know if it's the best on everyone, but... So there you have it. That's formal charge.